I'd like to introduce our next speaker, Gavin Schmidt, who's director of the NASA Goddard Institute of Space Studies, and today he's going to be talking to us about practical philosophies of climate modeling.
I'm here because I've been having over a few years a lot of very interesting conversations with Wendy and other people about how philosophers look at climate simulations, how they look at simulations in general, and a lot of those conversations have been very, very broad, very wide-ranging, and a lot of them have been kind of slightly unhinged from the actual practice of climate. And so what I would like to do is basically give an overview of how climate modelers actually think about what they're doing. And they're not completely naive, but they don't always correspond very well to how the outside world thinks what the outside world thinks they do. Okay, so a very clear disclaimer: I am not a philosopher. Okay, right? So that means that any philosophical statement that I make is not going to be properly referenced. It's probably going to be a little bit obscure, and if you're expecting logical coherence, you might be a little bit. I do aspire to use footnotes in as much detail as you can. Okay. This is a climate model. It's quite an old climate model. This is a single line of Fortran code for an old IBM 360 that used to be in our basement, and now, of course, is scrapped, and your phone has more power than this computer at the time, which was one of the 3 fastest computers in the world when it was installed. This is a line of code that we put together, and each one of those things is a subroutine, and that's roughly maybe 1,000 lines of code. Current models are running at around 500,000 to 1 million lines of code, depending on the center. So that becomes much harder to put into a box. The kind of scales that we're talking about are very important to think about. We're looking at problems that have scales from micrometers out to the size of the planet, and from milliseconds out to millennia. That's a huge scope. And if you think about what we can actually resolve from the top down, starting with the global picture, what we can resolve with a weather model is about that many scales. So you're kind of in the middle of the time scales, and you're kind of getting down to the kilometer scale of the weather. If you think about what you're not resolving, right, those are all the subgrid scale processes that, in some sense, if we think that they're important, we have to be parameterizing. We have to be coming up with phenomenological descriptions of the impacts of those subscales and seeing what impact they have on the larger result scale. Climate models in the 1990s had a much greater restricted view of that. In the 2010s, so that's the kind of CMIP era, we're doing a better job, we're going longer, we're going into more detail, but you can still see that there's a huge gap between what's resolved and the totality of the physics that we're trying to include. If you actually calculate what it would take to go from this to fill out that whole space at the current rate of progress, it could take us to the end of the century before we would get there. And so in our lifetimes, in our working lifetimes, we will always have this problem. We will always have the problem that the models have to make approximations, they have to make decisions about the scale at which they include physics or don't include physics, and how they approximate the things that they don't include. Right? That's a fundamental issue with any of these large simulations. In doing this, you therefore have a lot of ad hoc and relatively arbitrary choices to make. What scale do you what scale do you go up to? What do you include? What do you not include? Right? And so, given that need for approximations and parameterizations, model building in and of itself requires judgments. Right? It requires judgments, and obviously those are informed by our values, and they're scientific values, they're non-scientific values, and they are quite complicated. Those choices can be relatively ad hoc. You know, why do you choose this form of the parameterization versus that one? Why is it linear versus quadratic, etc. And quite frankly, they do involve non-epistemic values, right? So they're not just based on the idea, well, this is better science, or this is more theoretically correct. Now, the calibrations that go into these models obviously need to be transparent, and as a community, we are moving slowly in that direction, but it's very complicated, and there has not yet been an expectation that this is something that you need to document, and I think that this kind of goes back to Paul's point earlier on. The problem with people coming in and telling you afterwards that you needed to provide all of this other metadata is that they're telling you afterwards. If they told you before and there was an expectation that this was going to be required, then it would have been a much smoother process. Now, there's been some discussion, which I think Heather is somewhere here.
She's on her way home to Waterloo, unfortunately.
Oh, okay. Well, in that case, I can talk about her without her. And Merrick has made this point as well, right? That you know, is there a danger that the process of model construction, which is in itself a building of a specific theory of climate and encapsulating it within a code, is there a danger that people's social values, their preference or not for taking on risk or for policy prescriptions, is there a danger that those values are going to influence the coding that you do? And my experience of a couple of decades of working on climate models is that that fear or that concern is completely not valid. It's not something you need to worry about, because almost everything that you care about in these models is an emergent property, and I'll show you that in a second. And trying to control which ones of the tiny of the multitude of emergent properties that you might be able to fix by choosing a parameter differently is completely uncontrollable, and nobody has the time or effort or energy to do that in any kind of consistent manner. So what are we doing with the climate modeling? Well, basically we're starting with this idea of processes, right? Small scale processes that we can go and measure. How sunlight reflects off sea ice, how water evaporates from a lake, how the winds push around the ocean currents. And then we're going to encapsulate all of those different individual processes and put them all together. And then what we're looking for are the emergent properties of that whole networked system, right? And what we hope to find is that that produces a climatology, an average climate state, that not only looks like the real world, it also behaves like the real world. And not just in the mean, but also in the variability. Now, in and of itself, I think this is a hugely ambitious task, right? I mean, just look outside and see how complicated the climate is, right? It's a very, very dynamic and complex system. But of course, we're doing it, and we're being paid to do it because we're kicking this system quite strongly, and we would like to know what's in the box before it actually happens. So that goes directly to this issue of prediction and whether predictions are credible, and I'll get to that a little bit later. So here's a simulation from one of the NCAR DOE models. This is the map that you're seeing is atmospheric column water vapor. So you can see there's a lot of it in the tropics and less around the Southern Ocean and high latitudes. Each of these streams that you're seeing here, this is an atmospheric river of water vapor. These rotating vortices here, those are storm systems traveling in the Southern Ocean. You can see similar things in the North Atlantic. And as it moves into the summertime here, you can see spontaneous generation of tropical cyclones. Nicely kind of, this one's just about to hit. Where's it going to hit? Oh, Newfoundland, okay. Now, all of these patterns that you're seeing here are emergent, right? There's no subroutine that says make a make a tropical cyclone. There's no subroutine that says make these kind of interesting river patterns in the southern hemisphere. There's no subroutine that says rotate exactly around it. Right? All of those effects are a combination of all of the different pieces of physics that are in there, the dynamics, the evaporation, the cloud formation, all the rest of it. And those are the things that we're interested in. But you can see there's many, many different kinds of emergent behavior, right? So if I change something in the code that's associated with cloud convection, for instance, it changes everything, right? If I cared about the impact of cyclones, tropical cyclones in Japan, right, and I change the convection because I think that we should produce more of them, and then people will be more concerned about the impact of tropical cyclones. The chances are that it's going to change everything else as well, possibly making the whole simulation much worse, and possibly having impacts on things like climate sensitivity or rainfall intensity that will actually be completely counter to my idea about what it was that I was trying to do in the first place. So we don't do that. Right? We generally only tune or calibrate to directly observe data sets where we can. Okay, so models are perfect. Right? If you take a multi-model mean of surface temperature, there's actually a pretty good match to what the surface temperature does, and you look at the difference between that multi-model ensemble and the actual temperatures, then what you can see is that there are significant errors. Right? So here, the southern oceans are too warm. Particularly these areas here off Namibia and off Peru, they're very warm as well, and they're associated with a lack of marine stratus clouds that is a systematic and pervasive error in these models that has dated back for decades. If we could tune our models to get perfect climates, none of these things would be there. And so these persistent errors are indicative of a poor understanding of exactly why these features occur, or perhaps a poor understanding and insufficient physics at that time. So the question is not, are models perfect? The question is not, are models correct? Right? The question is, are they useful? Right? So, what are models useful for? Right? So, they're useful as conceptual test beds, right? So the concept of radiative forcing comes from GCM modeling. The concept, the explorations that we have of predictability come from GCMs. We can do hindcasting and attribution to try to explain why things changed in the past and for what reasons, right? And that isn't just for the 20th century, but also for the impacts of El Nino, what happened at the last glacial maximum, etc. We can quantify theories of climate change. I think this is one of the most important ones, right? It's all very well to wave your hands and say, well, it's dust, or it's carbon dioxide, or it's the wobbles of the Earth's orbit. But you want to be able to quantify that, because there are far more ideas than there are quantifiable tests of those ideas. And you need to be able to do it in a quantified way in order to kind of winnow out the ones that are not likely to be actually in place. And of course you can use them for hypothesis generation, right? So sometimes you see emergent behavior in these models, for instance, collapses of the thermohaline circulation in the North Atlantic, that we didn't really know very much about from the data, right? And then we can say, okay, well actually is this something that happens? Is this something that we can see? Can we find, for instance, teleconnections to El Nino events in the Pacific that we might not have been able to perceive just from the raw data itself. So that's a very important part of what models do. And then, of course, there's prediction. Now, I put this up here because I want to make it clear that models not being perfect is not actually a bug, it's a feature. Okay, bear with me. This is a picture from a paper by Benson and colleagues, and what it shows is the variability in the tropics at the surface versus the variability in the tropics kind of in the mid-troposphere. Right? So basically, this graph here is a measure of the coupling between stuff that's happening right at the surface, at the ocean surface, and stuff that's happening about 5 kilometers further. Now, this is the variance, right? So if you move up along there, then you would have more variance in the surface, and likewise more variance up the top. And you can see that all of the models kind of lie on a line, right? So that there seems to be a relationship in the model world between the variance at the surface and the variance aloft, right? And this actually looks quite tight. And these are multiple models, completely different, not totally independent, but a wide range of models that show that. Now, of course, this is a relationship you think, oh, okay, that's interesting. But of course, in the real world, there's only one number, right? So this is the real world, right? So this is one dot, a couple of estimates of that dot based on different data sets, but this is the real world here. So if all of the models were perfect, they would all have variance that was right there, right? And then I would not be able to say what this larger scale phenomenon was like. And then I wouldn't be able to say, well, how is that going to change in the future, perhaps, or how did it change in the past, right? It's because they have a whole range of variance. Some of them have too little variance, some of them have too much variance. But it's because they have a range and they're sampling a part of the space of plausible worlds that we can actually say something about the generality of the coupling between these two features, right? And it's because they're not right. It's because they have variance, because their imagery properties are not spot on. Okay. So let me make one point first. So no climate model is true, right? Climate models are not right; they are all wrong. Okay? No climate model is ever going to be true. So if that's what you're hoping for before you can say something about climate models, then that's not a very sensible thing to be talking about. And in fact, I would go further. No physical model of the real world can be true. And if you start talking about the truth of any kind of physical model, it's just going to get kind of complicated. And it's just that, you know, sometimes people do talk about physical models of quantum mechanics or of relativity as being true, even people who really should know better. But it's just more obvious that that's obviously a wrong statement. And it's more obvious with complex simulations where the disconnect between what's in the real world and what's in the model is stark. And so any discussion about climate models that relies on their truth or their confirmability is just not going to be very fruitful. Right? So let me be a little bit more specific about that. Binary concepts, where something is confirmed or not confirmed, something is falsified or not falsified, they're not useful concepts in this sense, unless you totally redefine those words to mean something else, which people are doing. And I think that they're much better replaced with frameworks based on an idea of they have varying adequacy for a purpose, or they have varying skill, and you can then judge how useful they are for you based on whether the models and that result is adequate for your purpose, or whether the models actually show skill, and I'm defining skill here as being a model result that gives better predictions than some naive alternative. Okay? These are both on a continuum, and something that's very, very skillful, like QED, is right at the end, and something that is not skillful at all, like astrology, is right at the other end. Right? So all of kind of normal science and philosophy kind of fits on that continuum quite nicely. Okay. So I'll give you an example. Here is a response to a volcanic eruption. Right? So what happens? Pinatubo went off in 1991. It put out a whole amount of aerosol into the stratosphere. Aerosol, small little particles, these are sulfate particles for the most part. That causes a radiation imbalance because these particles are reflective, so they're reflecting more solar radiation out to space than they had been the case, and so you have less energy coming into the system, about 3 watts per meter squared, less energy after about a year, and obviously if you have less energy coming into the system, one would anticipate that the temperatures are going to cool, and in fact they did. Right, so here are the actual temperatures, the blue and the green runs, and then this is the light-coloured ones are the individual model runs, and then this is the average of the model runs. Okay, and so you can see, oh yes, look, the model cooled right about the same time that the real world cooled, and so we can go further into this and we can show that it cooled pretty much for the right reasons. We can also look at the spatial patterns that you get when you have these big eruptions. This is the observed spatial pattern associated with tropical eruptions, and you can see this kind of a warm, cool pattern. This is in the winter following an eruption, and it's mostly a response in the winds to dynamical changes, or to temperature changes in the stratosphere. And the model produces something that's very, very similar. Okay? So we can tell, we can assess that the models here have skill over what you would have expected just from, I don't know, some energy balance calculation or something else. Now, one of the questions that is often posed is why do climate modelers seem to be pursuing this endless increase in complexity? Why don't we just stick to like easy, sensible energy balance models where we know all the terms and there's none of this complication and we can just use them? Well, the reason is because the real world is complex, right? If you just think about mechanisms by which solar activity might affect the surface climate, there's a whole ton of them. Some of them are just basic energy balance. Okay, that's relatively easy. But the UV change, which affects the ozone, which affects the temperature, which affects the QBO, which affects NOx, which is also affected by solar energetic particles that are absorbed in the mesosphere, which then changes the chemistry in the stratosphere, which also then changes the winds and the waveguides, which changes the AO and the NAO, which changes the surface in the winter and the seasonal wave that's different to how the SST was changing because of the TSI in the tropics. And then you've got something weird like galactic cosmic rays affecting clouds and ionization and aerosols. And there's no way that you can estimate the impact of all of those things if you're just looking at some kind of maximum entropy principle or some kind of top-down view of how climates work. All of these details matter. And when the details matter, you have to pursue complexity, otherwise you're not going to get hold of the right answers. So let me make a second point. A climate model simulation is a collection of multiple things, right? It's the code, it's the parameterization, but it's also a function of lots of auxiliary information, lots of in the auxiliary hypotheses, right? The forcings that you put in, the model physics, the initial conditions, where did you start, the boundary conditions, how big your mountains are. All of those things are part of climate model simulation. And so when you have a mismatch between simulations and observations, you can have multiple potential causes, right? You could have an error in the model, of course. You could have an error in the observations. You could have an error in the auxiliary hypotheses that went into building that simulation in the past. Okay. And of course, deciding on which one of those causes is the cause of your mismatch is something that is not obvious, and it does actually require work. And so I've done some reading in philosophy, so I know what that's like. So let's take the 20th century, right? These are hindcasts with the CMIP 5 models, which are in yellow, and the CMIP 3, which is an earlier version of that, is in blue. The observations are in black, and the multi-model mean is in red. And the spread that you're seeing here is mostly associated with internal variability, the timing of an El Nino event, the timing of variability in the North Atlantic or in the North Pacific or something like that. And that controls a lot of this year-to-year variability, which you can obviously see also in the real world, and that's obviously much more jagged than the ensemble mean, which basically follows the forcings, which in this case include volcanoes. Okay, that's Krakatoa, that's Pinatubo, but also the large increase in greenhouse gases, but also perhaps the slowdown in the 1970s and 1940s and 1970s that's associated with increasing industrial pollution from aerosols. You can compare a run like this, which has all the forcings in as best each of those model groups was able to put it together. Now, each of the model groups had different estimates of the forcings, particularly the aerosols. But you can compare that to the natural forcings case, where there's only basically volcanoes and solar variability, and you can see that there's a very large difference. And in fact, that this is a detection of climate change, this is a detection of anthropogenic climate change, because this is way outside what we would anticipate is the PDF of where we would be in a purely natural world. And so it's kind of interesting to see, right? So this is about 1 sigma, 2 sigma, right? This is over 5 sigma in terms of how outside of our expectations it is, which is useful when you're talking to physicists. Now, there are some interesting things here, right? So where does this line, where do these lines come from, right? Well, remember, they depend on relatively uncertain emission data sets, aerosol concentrations. They depend on the completeness of the forcings, which is always unclear. And they also depend on how sensitive any of these models are, and they have a range of sensitivity. And then you've got all this up and down stuff here, which is associated with the internal variability. So there is a big range here between, for instance, if you were just looking at the temperature in 2010, right? There's a big range of model estimates for what that temperature might have been, right? The average of those is actually quite close to where we are relative to that pre-industrial mean. But the models have plausible variations that could have caused it to be quite a bit less or quite a bit. So how do we go about evaluating that, right? So this is one data set, but the reason why the models have produced this response, it has to be physically coherent inside the models, right? So there must be physically coherent other aspects of the climate that we can then go and look for in the real world. And one of the most important ones, of course, is that since this warming has been driven by a radiative imbalance, that radiative imbalance implies there is energy coming into the system. Where is that energy going? Almost all of it is going into the ocean. And so one of the ways to evaluate these estimates is to see what their estimate was for the total change in ocean heat content over this period, and then compare that to another data set which is independently derived. Okay, but there's one little thing here which is kind of interesting, which kind of goes to that underdeterminacy issue, which is this small apparent departure that's going on here between the model mean in both CMIP 5 and CMIP 3 and the observed temperatures over this more recent decade. Okay, so what's going on there? Okay, so this has been called the hiatus. And remember that all of those model runs, okay, there are multiple things that go into that, right? So you have the internal variability, you have the forcings that are driving them, you have the model sensitivity, but then you also have, well, what am I comparing things to? I'm comparing things to an observational data set. Is that an observational data set that is a totally commensurate observational data set with what I'm producing from the models? Okay, so the answer is no. I'm not sure of the question. What's the question?
Where's it coming from?
Where's it coming from? That's not a yes/no question.
Does the output match the data with the question?
Okay, so yes. No, yes. Okay, the point being is that the forcings were not correct. So we have good reasons to think that we were underestimating. This is the volcanic forcing, this is the solar forcing, and then this is an estimate of what the aerosol forcing has been doing. So we did some things wrong, particularly from about 2000 onwards. We had some estimates of the internal variability that you can account for. Basically, we had a lot of La Niñas as opposed to El Niños. You can account for that. And then you can also account for the non-completeness of the data set that we were comparing things to. And when you do all of that, you basically would implicitly shift that model ensemble from where you see those blue lines that blue set to these kind of the dotted grey lines, and this would be your this is the corrected observed data, and then this would be what you would expect, right? So you can reduce the discrepancy by 5 different ways, such that there isn't so much of a discrepancy. So those are all independent, right? They all occurred kind of coincidentally. It wasn't obvious that both volcanoes and solar would go down in the same direction over that decade, and the whether we have El Niños or La Niñas, that's a random thing as well. So what we have is basically 5 things conspiring to make a discrepancy rather than just one. Okay. Now, there's been some discussion in the literature about simulation as a third pillar in science, right? On top of theory, experiment, simulation. Right? Is that a third pillar? And people either are for that or against it. It seems to me in a rather religious manner. And I think this is a very good statement. People have, I think people will acknowledge that all layers of science now are very computational. Theory is very computational, experiment is very computational, and simulation kind of sits in the middle of that. And I think that there are some really good examples of where simulation is really very much in between theory and experiment. And I'll give you one example which kind of touches on something that Paul said earlier on, which is the question of reproducibility. When we run a simulation, right, on our computers, in our systems, we ensure that it is bit reproducible, right? So if we have to stop it and we have to start it again, we can start it again. It's exactly the same as it would have done, and there's no divergence whether we repeat it. And we can repeat it a number of times, and we will get exactly the same answers every single time. But that requires not just the same code, but it also requires the same compiler, the same computational environment, the same libraries, and the same pseudo-random number seed for any stochastic things that you've got in there. But that means that all of that stuff from those databases, CMIP3 and CMIP5, is actually, in effect, unreproducible. Because nobody can go back and recreate that machine hardware, those compilers, the bugs that were in the environment, etc., etc. And so those results are actually irreproducible. In the same way that a laboratory experiment done 10 years ago cannot be exactly reproduced. Right? You cannot keep exactly the same conditions and the same temperatures, humidities, and all. So is that a problem? Well, is it a problem for laboratory science? No, because what you do is you redefine the notion of what it is to be reproducible. The issue is not can I produce the exact same data, but can I reproduce the same phenomena that I'm actually interested in. Right? And so that notion of reproducibility of phenomena versus data is really at the heart of the difference between theory and experiment, and actually simulations lie much more on the experimental side versus the theory side. Okay. So now we come to predictions, right? And so I think this is a great quote. If we had observations of the future, we obviously would trust them more than models. But unfortunately, observations of the future are not available at this time. So that's probably always going to be true. Okay, we're interested in predictions. We have to use models to do predictions. What does that mean? How do we build credibility in those predictions? Right? How do we assess whether these are predictions that we should be paying attention to? So, in talking about this to many people and having thought about this for many years, what people actually do is they have a set of heuristics that they use to assess whether a phenomenon that they're seeing in a climate model is actually something that is worth telling to somebody else or acting. The first thing is, does that result make any theoretical sense? Right? Sometimes you can be surprised and you can go back and think about it and think, oh, and other times it's just crazy, right? And so that's a sanity check. One of the things that we do look for is whether a result appears in multiple models. Now, we talked a little bit earlier on about whether model agreement in and of itself was a useful result. I would say yes in this context, because if and it goes to that idea of reproducibility, right? The basic assumptions that we're building into those models, what we want them to be is coherent. Any implementation of those basic assumptions is going to have errors, is going to have ad hoc elements to it, judgments that went into it in different GCM groups. But what we want is a result to be a reflection of the basic underlying physics, not the individual implementation of that physics in anybody's individual model. And so if a model result is common across a lot of models, or there's a very obvious reason why it's in some models and not in another, that's actually a useful thing to know. Is there support in the observations for this result? You know, we've had some climate change, not as much as we were expecting, and we have a whole history of climate change over the history of the Earth. You know, we should be able to find some support for your result in the observations. And of course, do these things match in a quantitative sense? It's all very well for one model to say, oh, there's going to be a 100% increase in major hurricanes with a 1 degree temperature change in the global mean. But if your data only says that there's been a 1% increase, I think you've still got a discrepancy there, and that's still not a robust result. But you have to be a little bit careful about what it is that we're trying to predict and what sources of uncertainty there are in predictions. And I think this is a nice graph that demonstrates that. So this is a graph of summer sea ice extent. This is from the hindcast that I showed you. This is 2000 there, and so these are the projections going forward. Each of those different lines is the ensemble mean under a different scenario, so a different estimate of what greenhouse gases are going to do in the future. So that uncertainty there, like that spread, you know, from here where I think this is a commitment run, so no further changes in carbon dioxide, for instance, to this one, which is a very steep increase in carbon dioxide. That's the scenario uncertainty. Now, for a climate modeler, that's irreducible, right? I'm not in any position to predict what the economy is going to do, what technology is going to be invented, how people are going to decide how to produce energy and to farm and run their lives. Okay, so that's, for my part, that's pretty much irreducible uncertainty. Now, for any one of those scenarios, right, so take this blue band here, this spread in the sensitivity that you're seeing across different models, that's structural uncertainty, right? That's the fact that different models have different sensitivities because they have slightly different balances of all the different physical terms. Now that is reducible, because if we had a perfect model, that should go pretty much to zero. And then you've got basic either initial condition uncertainty or weather uncertainty, just the fact that the system is dynamic, it's complex, and there's a lot of internal modes that are going on that you can't predict beyond beyond 2 weeks for the weather, beyond 6 months for ENSO, and perhaps beyond a couple of years for something like a returning stream function in North Atlantic. And so you've got three very different sources of uncertainty, some of which are intractable, some of which are mildly predictable, and some of which are reducible with a little bit more work. And then, of course, you've got the real world, which tells you that we don't know everything about the system, right? So you know, you can't expect that the models cover everything that's happening. But I have to say that with 2014, it looks a little bit better than it did. But the point being that this is way outside of what we anticipated, and that implies that our estimates of the structural uncertainty, if you just take them from the spread of the models, is almost certainly totally insufficient. So how do you quantify this structural uncertainty? That's too from what I was saying, so there's kind of practical heuristics, the people's building of credibility as a function of, how many processes you're incorporating, how well they perform, what the emergent behavior kind of looks like. It means that we should be interpreting, and in fact we do, interpret climate models in a very kind of informally Bayesian way. Right? So we have an expectation that they're either good or they're bad, and then they have demonstrated skill. Where there is demonstrated skill, we basically shift our priors towards the results. So for things like the global mean temperature over the 20th century, you might not have started off thinking that we were doing that very well, but actually we are doing that quite well, and so you might be able to shift your expectation that we actually are able to predict that clearly. And so you can base these kinds of posterior PDFs on these elements of skill, robustness, etc. But of course, it's still a little bit of a work in progress, and because this is done in a rather informal way, it's totally unsatisfying to the more mathematically inclined basis. And so I'm happy to say that we're working on making that into a more formal thing, but that's still a work in progress. But let me give you an example of building credibility and skill. So as part of CMIP 5, there were a number of model simulations that were based on Paleo-climate examples. So they said, well, let's do the last glacial maximum, right? Let's do the, this is only LGM. So let's just do the last glacial maximum. And then people said, okay, well, are there elements of the climate system that are robust between really, really cold climates, present day climates, and really, really warm climates that we expect in the future? Right? And so these are the relationships here between the temperature differences over the oceans versus the land. So basically, when something changes, is there a relationship between the land and the ocean change? Right? And here are the answers for the warming runs. Right? So this is when you increase carbon dioxide. You can see that there are differences in the magnitude of the warming, but they all lie on a line. Right? The relationship between the land warming and the ocean warming is actually pretty constant across a whole suite of models in warm climates. Now we can go back to the LGM, which is a cold climate, and you can see that, again, even though the models give different degrees of cooling for the LGM, all of them lie pretty much on that same line. Now, the neat thing about climate models of the past, or modeling of the past, is that we can actually go back and see if there's any data that supports that. And so these crosses here are the estimates of the data for this exact same quantity. And these are sampled in the places where we have that data. And so we can go back and we can say, look, there is a constant and robust result here that we can actually test and demonstrate that in the LGM, this was a skillful prediction. And so that gives you some hope that these changes, which are predictions for the future, are also going to be credible. And you can do this in a number of different ways. So let me conclude. I view, and I hope that you would agree, climate models are coherent possible worlds with, in many, many respects, very similar phenomenology and emergent properties to what we observe in the real world, not just in the modern day period, but over time as well. I would therefore argue that they are actually useful for a lot of things. But the proof of that does not fit.
Thanks, that was a terrific talk. So I took a significant part of what you were talking about at the beginning of the talk to be sort of directed at me, so I wanted to...
not just you.
Right, well, but in particular, I wanted to sort of highlight a difference between my view on that stuff and Heather's, and where I think some of the stuff you said actually supports my view pretty well, right?
Of course.
So, yeah, okay, good. So, you granted a variety of premises that I think are the ones that I need, right? Namely that making climate models involve judgments. They're judgments about the skill of the model. That skill of the model comes in degrees, and that the degrees in which it comes are not univocal, right? That they could be skillful at this rather than that, etc. Good. And then you said, well, is there a danger that we're, and I can't remember exactly what you said, right? Is there a danger that we're doing some sort of thing, and the proof that we're not doing that thing is that there are all these emergent behaviors, namely that we can't predict exactly what all this stuff is going to do. So do we, if we want more, do we try to get more tropical cyclones in Japan by turning this dial? No, we can't do that because all kinds of unforeseen things would happen. I totally agree with all that, right? And I don't think that's at all in tension with what I've argued. And right, in particular, what I think is right is that judgments like that are made all the time. Those judgments reflect people's, at the time, what they perceive as the relevant metrics of skill that are important, and that they have wildly unforeseen consequences in what other kinds of emergent properties that can result. And so in particular, right, some people in the science and values literature say, well, because these kind of judgment calls that might reflect inductive risk judgments or whatever play a necessary role in science, we ought to make sure that people are making the right value judgments or whatever. No, and I think exactly all the things you said are right. Those show that those judgments you make, this metric of skill is more important than that metric of skill, so we're going to try to succeed at that, are going to have all kinds of unintended consequences. They're going to get kind of buried in the models later on. And yeah, there's going to be lots of these kind of value judgments buried in the nooks and crannies of the models in all kinds of unforeseen ways. But that doesn't mean they're not there. The argument was never that there's a worry that people are sort of gaming the system to get more tornadoes in Japan or something. The claim was just simply, right, that value judgments get made. They're not, as you said, right, they're sometimes non-epistemic value judgments, and they have lots of unforeseen consequences in the models. So, good, right?
Yeah, I mean, but so the corollary of that is that, the results of the models are therefore horribly contaminated by those value judgments, and therefore we dismiss the models because of those.
That was never supposed to be. I don't think that was ever supposed to be enforced.
So you might not be claiming that, but other people are, and we get this thrown at us. And so, I mean, my point is that even if you were trying to game the system, you would fail miserably. And my experience as somebody, I mean, I run a model meeting every 2 weeks. In 20 years of doing this, I have never seen somebody use a totally outside of a social value, let's say, to suggest that we change a parameter or we include some piece of physics or not some piece of physics. Right. So what I wanted to do was make it clear that there are judgments that are made, but they have nothing. Like one of the statements, I think it was from Heather, was people making judgments because of their feeling about risk, and they might change something in the clouds in order to increase the sensitivity so that people would be more concerned about carbon dioxide. Right? So none of that, in my experience, ever happens. I just want to make that clear.
So, sorry, we have quite a long queue already, so if we could just keep the questions quite succinct, and we'll save the follow-ups for discussion after. So,
which I'll be happy to do.
Stan has the next question.
Now I'm tempted to follow up on the exchange we just had, but maybe I'll save that for lunch. Make a quick comment and then ask, hopefully, a very simple question. So the comment, first of all, so I'm interested in this list you had at the beginning of the different things models are good for. And the comment is, if you think about whether or not the model should be, in some sense, relevant to public policy, that can add sort of a horizontal dimension to things. Because a model that might be good just for internal scientific use might not be very good for public policy purposes. That's just a comment. And then the question I wanted to ask, looking at these different things that models are good for, could we have different models that are good for some of these purposes and other models that are good for others? So for example, an energy balance model might be good as an conceptual framework, even though it doesn't make very skillful predictions.
Oh yes, totally. So I mean, Isaac Held wrote a very nice paper about this on the hierarchy of modeling, and made the very sensible point that yesterday's fully complicated and equipped GCM is totally discarded as soon as we have today's complicated and better GCM. Right? Whereas something that is an energy balance model or a QG approximation or dry dynamics or something like that, that pretty much always stays the same because it's a closed system and you're trying to find something that's just like that's okay. Well, what can I explore using that dynamics? What can I explore using that energy balance? And people are still using all of those different models, and they're not using a CMIP 3 model, right? And in CMIP 6, they'll stop using CMIP 5 models. Right? So, but to inform that hierarchy of of different approximations, effectively, you need to have ever more complex models that have more and more stuff, so that you can see whether those results are actually robust. So you can see things in the GCM, and then you go, oh, I wonder what the basis of that phenomena is. Extract that out, imply it in a less complicated, less featured model, and demonstrate that actually 90% of what you saw in the GCM was because of this particular kind of dry dynamics, right? Or was because of the energy balance, or was because of something else. Right? And that's a really good part of how you interpret GCMs, right? You interpret GCMs using kind of lower level heuristics, some of which are based on less featured models, and that's how you go about explaining what you see in the GCM. So I think that's the answer is yes.
Jim has that question.
Thanks, Gavin. I just wanted to ask your definition of your term, better predictions, especially when they're outside of our lifetimes. It's a 2100 prediction. You used the phrase better prediction. What do you mean by that? Or how do you judge a better prediction?
So what I'm talking about is more credible predictions, right?
Okay.
So I would like to think that more credible predictions in the future are actually going to be more likely to be true if the scenarios end up looking like the ones that we've been running, which is of course irreducible and so. The mechanism by which you make a prediction matters, right? If I just 40 please, okay? That has no credibility. Nobody here was convinced that that's the right answer. Right? So, demonstrating that the system that you have is capable of matching out-of-sample results in the Paleo-climate runs, that goes a long way to demonstrating that their overall sensitivity is not that far off. Right? Where there are ranges of sensitivity, right? I could use this example as well. So for instance, we're worried about sea ice melting. In the early Holocene, seasonal sea ice was much less than it is now. So there was probably summer ice free conditions around 6,000 years ago. Right? And there's a lot of evidence around the Arctic that those were very warm periods. There are beaches on North Greenland that are now totally covered in ice, and that there's no way actually to produce beaches, and there hasn't been for thousands of years. We are also testing the models in those situations. Right? Some of the models show a very large change in the sea ice, and some of them show only a very small change in the sea ice for those conditions. Those models also correlate with their prediction for 2050 or for 2100. Right? So the less sensitive models were also less sensitive in the past, and the more sensitive models in the future were also more sensitive in the past. And so I can, by looking at the past, gain some idea about which models are going to be more sensitive, which models are going to be more correct than others, and then weight my predictions accordingly based on the idea that there is a correlation between a skill metric in the past and a skill metric and a prediction in the future. Now, the reason why that doesn't happen very often is because most of the skill metrics that people have looked at have been for the modern day period, seasonal cycle, inter-annual variability, response to ENSO, blah, 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 blah. And it turns out that those don't correlate to different predictions in the future at all, right? Which is surprising to many people, like Reto can show you some more examples of that. And so if you're going to have more credible predictions for the future, you need to be testing the models in out-of-sample cases that have changes that are commensurate with the size of the changes that you're predicting for the future. And so one of the things that I push a lot is the use of Paleo-climate to do that, because nobody is tuning their models to get a better seasonal cycle or a better response to the OGM, whereas they are doing it to get a better seasonal cycle.
Thanks. I actually want to stay on this question of the comfort we can take from prediction. So the nature of the problem prevents real, true out-of-sample prediction, and that's not our fault, and that can't be held against us. It just means that it's a different problem. But it does weaken the comfort we can take from in-sample prediction. So you mentioned Pinatubo. When I was a GIS, runs were made on El Chichon. It turned out that when they refined these runs, they found a bug in the model. Okay, so with another volcano, it didn't work. The way I usually tell this story is an accepted paper was pulled. This is a good story, right? But it also means that the El Chichon story was, and the El Chichon story was never published. So given that when we fail with one volcano, we fix them, I don't know if you want to call this tuning, but we fix the model, then in that case, how do we interpret, how do we take comfort from the success with El Chichon, with Pinatubo? I mean, do you see what I mean? This is the basic thing of in-sample. We do one volcano, we find a bug in the model, we fix it, that's good. We pull a paper, that's good. We do another volcano, also in-sample, it seems to work, and we want to use it as evidence that things are right. How do we square that?
So I'll make two statements. One, the first simulations we did for Pinatubo were immediately after the eruption went off, and we had the first estimates of how much sulfate was being put in the atmosphere. That was a totally out-of-sample prediction of how much the world would cool before it happened, right? So that we can do out-of-sample changes, real, true future out-of-sample cases when the forcing is larger. Okay. So first, second thing, we're not just looking at one thing, right? So the winter warming pattern that I showed you after the Volcanic pattern, nobody had ever looked at that while we were building the model. Right? That was new data.
And it's the only thing you looked at.
What do you mean, the only thing
I mean, there's no sense in which you looked at something else which didn't work, and
No. In terms of target data against which we can test responses, we are very data poor, right? So generally speaking, we will look at all the data that we can, and we will publish almost all of those comparisons. The winter warming pattern that's associated with this change in the winds, that was new information that was produced after we had run all of those experiments, and this is a post-hoc analysis. The same thing is true with the ocean heat content, right? So there were the first time that somebody had put together a time series of the ocean heat content, it was horribly contaminated with non-climatic things. But when we compare and then people said, oh, well, let's compare it to the models that we've already run, right? So it's an out-of-sample prediction because the data wasn't available when we were building the model, right? The data existed in some sense, but we didn't know that. And then there were discrepancies. There were large. There was this huge feature in the 1970s where the ocean heat content seems to do this like big oscillation, and none of the models produced it. We looked at sampling issues. We looked at parameterization issues, and it was hopeless. There was no way that we could match it. Big puzzle. What happens? The oceanographic community said, oh, actually, all of that is associated with these XPTs. They have the wrong full speed in them, and if you fix that, and then you make all these different corrections for the engines and the blah 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 blah, and now here is our new refined estimate of the ocean heat content. Again, totally out of sample for our purposes. It turns out to match all of the data that we've been producing all along. Right? So if you get something right for the right reason, you will see things like that occur. And those are actually, to my mind, great credibility boosters in the whole system. And it doesn't happen every day, but when it does happen, it's very cool.
So we have 3 minutes and 3 questions, so let's
Okay.
try to have yes/no questions if possible. This one comes from live stream.
Yeah, so we have Gregor asking, so Gregor Betts, and he says, thanks for the nice talk. You said at one point, you can't read off structural uncertainty from the model spread. That would be insufficient. So do you agree that we should interpret the results of the MME as a lower bound to the uncertainty we face?
Can I use maybe? So I think the answer is no, because there are some cases where you're going to see a spread in the structural uncertainty that is not related to real physics, and it's a function of weird stuff going on in the models. Right? So, for instance, a lot of the models have a relatively low top, right? So they don't go all the way up to the top of the atmosphere. Anything that you're looking at there in terms of trope exchange, there's a significant bias, and there's also a bias in variability as well. And so I wouldn't want to make a very general statement along those lines. Though I am, I think his point is well taken, but I don't need to be completely religious.
Rob.
This is hardly a yes/no question. Right. So, like your talk, like your list, but I was sort of a little disappointed because when you got to sort of the end and talked about prediction, it was mostly averages of slow-moving things. Like global temperature. But so from the sort of things that we draw, and the book I described yesterday from the cosmology, which say involves how do you invest billions of dollars to make water systems more resilient. I mean, you care some about the means, but you care a lot about the extremes.
Sure.
And you care a lot about large-scale correlations, temporal, and things like precipitation.
Right.
And so we've got this system which you describe as very emergent. We're forcing it very hard and outside of data that we have. And we're trying to make use them to inform policy decisions. We're interested in extreme behaviors in such a bounding cases.
Right.
So give me some confidence in that, as opposed to the global mean temperature.
Oh, yeah, so that specific case, people who are using that data have to build the credibility argument for that. Right? I mean, for all of the things that people could be interested in terms of public policy, I cannot do a study that says that that's a credible prediction. The people who want that data have to be able to do that themselves. Now, we're building systems that should allow them eventually to be able to do that, but you have to build credibility for the particular metric that you care about. Right now, I've talked about global means, I've talked about sea ice, I've talked about dynamical patterns. I'm not an expert in modeling of water systems in the Colorado Basin, right? So I can't tell you myself that that's a credible set of data that you're using. That has to be part of your system. How credible is the data?
I told you the climate parameters I need, which is I need to know. That's a question.
No. I mean, that's all.
Can the models tell me about essentially, bounding cases on how long it cannot rain over how large a region on the western United States? So that has nothing to do with anything other than the climate model.
Okay, but to build credibility in that, you have to examine a number of things. Okay, first of all, what is the statistics of that in the models? I have no idea. Somebody would have to look at it, right? You have to pull out that information and see what the spread is of that variance. And now you say, okay, well, is there any data that you can use to support both that background level of what that background PDF is and perhaps how it changes as a function of forces? Well, actually there are. So there's great tree atlases for your region that go back 1,000 years, right? You can infer from them statistics about droughts, and you can try and infer whether there's any evidence that these are false. Now, people have done that, and there's no apparent evidence that that background variation is being false. Right, so you can say, okay, well, what's that PDF? Is that the same PDF that you see in GCM control runs, or the GCM and last millennium runs have been done runs from the last millennium. And then you can say, okay, well, how do algorithms match? What are the extreme values look like? And then see, okay, is this going to change in the future, or can I use the same envelope from the past that I've been using up until now, right? There are ways in which you can do this, but I can't tell you what the answer is without me doing it.
Okay, so we're going to have to wrap it up here now, but we're going to take a break. It'll be about 5 minutes, so I encourage you to stay seated while we set up for the next speaker, unless you have to go to the washroom. So please join me in thanking Gavin.